There's nothing more rewarding than working in the space field. It's a fantastic area to work in. There's always something new. I've had to learn, starting out as a physicist, becoming a roboticist. Also had to become a manufacturing engineer and a chemical engineer. I've worked in astrobiology. I've had to learn about microbiology. It's just the whole of the universe is open to you. And that's an absolute privilege. And that's one of the wonders of working in this field because there are no experts. You're never standing still. You're always constantly learning new things. And that's what makes it so much fun.
Hi, welcome to the Sunfiber channel. This is Alan, and with me today is Alex Ellery, a professor at Carleton University studying robotics. So, Alex, could you tell us a little bit about yourself first and your area of
Yes, sure. I'm a professor at Carleton University. My area of expertise and interest is basically space robotics, first and foremost, and I'm a roboticist second. But in fact, I've moved away from the robotics side of thing into the space mining side. So I cover quite a wide range of areas. I originally started off focused on Mars astrobiology, development of scientific instruments, the robotic deployment of scientific instruments to search for life on Mars, and drills, and so on and so forth. And then I carried that on when I came over to Canada. I was originally from the UK. And I carried on doing the same sort of thing, focusing on rovers in particular and the development of rovers. My group built a micro rover for the Canadian Space Agency, which never flew, but it had essentially a path to flight. Then I started getting into the various other things like drills and Raman spectroscopy. And then about 10 years ago, I started getting very interested in situ resource utilization, which is a NASA-EASE term for space mining or moon mining or asteroid mining. So that's really been the dominant activity. Well, it started off as a kind of side craft, and now it's morphed into my main activity. So very, very rapidly started to become my main focus. I'm interested in some rather unusual concepts. One particular one, which has obsessed me for many years, is the concept of a self-replicating machine, or otherwise known as a universal constructor. And this is the goal to which I'm working, to try and develop something like a self-replicating machine that could work on the moon and then essentially industrialize the moon very, very quickly and at
Right.
no cost. And so that's really my focus. Yeah, that's it. I don't do non-space work. This is basically, this life's too short.
Okay, sounds like a good idea. Okay, so then how about you give a vision of how your robots would work in space mining?
Right. We developed this micro rover called Catvic, which is actually an Inuit word meaning wolverine. The reason for that was that wolverine is a very small animal but incredibly aggressive. So it punches above its weight is the idea behind it. So Catvic was a 30 odd kilogram rover, depending on what we mounted onto it. And it was capable of long traverses. I mean, kilometers, quite a few kilometers. We tested it for several kilometers. So it was very successful. Again, it was quite a while ago.
How far along was this to building a self-replicating robot?
Oh, quite
Like,
far away. The thing about building a self-replicating robot is that there have been several papers written on self-replicating machines. I take a particular view on how to do it. And for example, I don't know if you come across Phil Metzger, and he and his group wrote a paper a few years ago about industrializing the moon and then turning that industrialized system into a self-replicating system. I don't think that's feasible for several reasons. First of all, the closing of the self-replication loop is going to be very challenging. So if you can imagine, let's say you have a mobile phone, you want to make it self-replicating. You have this huge fan-in of inputs. You saw different materials, different processes to manufacture those materials and components, mix them together and then assemble them. And if you want your machine to self-reproduce, it then has to reproduce all those machines.
yep.
So in order to do that, what you want to do is you want to narrow that fan-in as much as possible. And so you want to minimize the number of the different materials you use, and you want to minimize the number of processes you use.
Right.
So this is where the space mining comes in. We're trying to replicate in many respects how the origin of life. Now, if you look at the biological cell, it's an extremely complex thing with a very complex architecture. But before you can actually put together a cell, you have to have evolved all the individual components. The ribosome is actually a very complex machine, but that's key to how a cell works. So
Okay.
these have to evolve to a significant degree before you can get any kind of cell working. So we've taken very much the same view. There are certain components we need to be able to manufacture with a self-replicating machine before we can even begin to start looking at the architecture.
Okay.
And so, if you look at this, this insight goes all back to John von Neumann, who originally came up with the idea of a self-replicator. He was looking at logic and the maths of it. And he came to the conclusion that you need four parts to it. There are four fundamental parts. So, first of all, you've got your program, which in biology is called the genetic code. That's your instruction set. And then you've got your copier, which can copy that genetic
Yeah.
code. And then you also have some kind of mechanism which basically implements that genetic code. It reads the code and then implements it and then builds according to that code. And the key to that is having some kind of actuation system, like an arm. So it basically acts in the environment and then picks up components and puts them together. If we
Right.
take that logic all the way back to fundamentals, what is a robotic arm? It's basically a particular pneumatic configuration of motors. So this is why we focused on motors. Motors are the core component. With motors, you can build any type of machine. You can build a lathe or a milling station or a CNC machine or a 3D printer. They're all particular configurations of electric motors. So one of the things we did a few years ago was to essentially 3D print an electric motor. We did that, and that was just a proof of concept to show that a complex mechanism like an electric motor could theoretically be 3D printed. Obviously, we were using plastics, which you don't get on the moon, so that would have to be adapted. But this was the first proof of principle. The hardest part was actually the coils to wind around the magnets. But the magnets were manufactured by Oak Ridge National Laboratory for us for this particular purpose. We've since then had magnets 3D printed for us by Waterloo here in Canada. So the idea is to try to do one of two things. One is to generate the proof of principle that an electric motor can be 3D printed. It was also to look at some of the problems in 3D printing electric motors where maybe not just a 3D printer, we may want to add some additional kind of manufacturing capabilities,
Right.
like a milling head and things like that. So one of the things we've been looking at is building an integrated 3D printer which also has a milling head in it. But we've already demonstrated that you can take silicone plastics and you can melt aluminium on them. So potentially you can create insulator and conductor in the same machine. We demonstrated that using Fresnel lenses, but we
Oh,
haven't integrated that into a printer yet. That's a future project. So we've been exploring these ways of trying to put together various capabilities. We've been focusing mainly on the difficult things. So
yeah.
if it's hard, we focus on it because we regard that as key. It's pointless playing around the periphery. Another aspect, of course, is electronics. How do we manufacture electronics, particularly on the moon? On the moon, we're not going to be doing any solid state manufacturing anytime soon. If you look at the tolerances, a typical metal alloy, if you're doing metallurgy, typically you're going to be talking about purities of 0.01% maximum. If you're looking at trying the purities required to build a silicon chip, you're talking about 10 to the minus 9. So it's
Yeah.
orders of magnitude more difficult
Oh, yeah.
to try and build solid state electronics on the moon. The approach I've taken is very much a case of what do we want to achieve on the moon? But most people, when they're looking at in situ resource utilization, they're fairly open ended about the application. They say, okay, we got stuff here, we can extract metal, we can extract iron. And say, okay, we got iron, fantastic, and don't think any more of it. We can use that for all kinds of things. What I've done is started to trying to do a mapping. So we have something called demandite. This is what we want to be able to build. We want to be able to build electronics. We want to be able to build motors. We want to be able to build structures of various kinds, insulators, conductors, thermal insulation, thermal conduction. We want to have all these kinds of things. if we want to build an entire spacecraft on the moon, what functions do we need to build a spacecraft with all the subsystems, from communications to thermal control to electronics and so on and so forth?
So a spacecraft that humans could use.
Yes, a robotic spacecraft in essence. What do we need to achieve? What functions do we need to achieve? And then map that to what's available on the lunar surface. We want to have electrical conductors. Unfortunately, there's not a whole lot of copper on the moon, which is what we normally use for electrical conduction, but there is a fair amount of aluminium.
Yep.
So we can substitute by regauging, we can substitute aluminium for copper. And so taking this approach, saying we don't have this on the moon, but we can still implement a function. It may be suboptimal, but it'll work.
Yeah.
And
My
so,
my last house actually had all aluminum wiring.
right,
Instead of
okay.
copper.
Is this not knob and tube?
No, no, it was like built in the 70s, but
Okay,
it was
okay,
aluminum wiring instead of copper wiring, just because aluminum was so much cheaper in the 70s.
right, okay. Well, actually, this brings me to knob and tube technology because this is quite an interesting one. Because in knob and tube technology, they don't really use much plastic for
No,
insulation. They use glass fiber. They use fiberglass, and they use
oh, right.
and porcelain for the junctions. I was inspired to use this old technology and figure out, given that there's hardly any carbon on the moon, or very little of it, we can't manufacture plastics. What can we use instead? And of course, the answer was from knob and tube technology. We can actually manufacture porcelain from lunar resources
Yes.
and glass fiber and so on. So it's actually trying to figure out how do we implement the functions that we need to do by going back to basics. And
Right.
rather than trying to shoehorn terrestrial technology and then putting it on the moon, making it work, what we do is we try to say, okay, what's available? So imagine we're an indigenous tribe going to the moon and we have to survive on what's available there.
Yep.
And we don't want to waste anything, but we want to maximize the use of what's available to us and create a technology which we can build from the moon using the moon. And so it's a different approach to what most people who work in this area are doing. They're saying, okay, we need iron, we need this, we need that, and we can manufacture it, and hopefully we can find some kind of use for it. What I've been trying to do is saying, okay, we've got all this material, and here's how we can use it to implement these specific functions that we're going to need. But there are some obvious problems. One is electronics. As I said, we can't do solid state on the moon, or at least anytime soon. But there are alternative technologies. We've gone a little bit steampunk. Instead of using transistors, we go back to vacuum tube technology.
Oh, okay.
So vacuum tubes are very simple in construction. You got your cathode.
Vacuum's pretty easy on the moon.
I wouldn't call it easy, but I mean, at least the material resources are there and we can access them.
I mean, to actually get a vacuum, at least
The
what we
vacuum
call
part, yeah,
it.
that's the easy bit. Yeah, the rest of it isn't necessarily quite so easy. The
Yeah.
manufacture of the vacuum tube itself is a bit of a challenge, but it can still be done. The various materials to do it are there. Now, if you build a modern CPU out of vacuum tubes, it'd be the size of a huge block of flats and not very useful. We've gone the other way. So this is why I say it's steampunk. We're taking an old technology and then adapting it with a new technology, which is neural networks. And so we've been building analog neural network circuitry to implement fairly simple rover behaviors to show that we can build new types of computing devices using physical neural net circuits. So again, it's trying to adapt to this new environment and actually exploring what we can do. Almost certainly will involve trying to figure out how to implement electronics in a different way than we do currently.
So, like neural networks, they usually say you need like a GPU and
Yes, because they're in software.
yeah,
There's two ways to do this. One is to design your circuit so that, on the ground, so you know what your circuit looks like, and then you build it. It does no further learning.
right.
So it's already configured to perform a particular function. The other thing is that one of the things I've been looking at is the octopus. We tend to focus on single, actually not now, we have multi-core architectures now, which is more like octopus-like, because the octopus has 9 brains,
Oh,
eight,
okay.
each brain in its arm and plus one central brain. So it's basically what I don't know much about the octopus, but what I've been reading about it, obviously each arm brain controls the arm to a very high degree.
Yeah.
And so a lot of the complex algorithms are generated in each individual brain around the arm. The lesson there is we can separate out different computational functions to serve different purposes and thereby keep the size of the neural nets relatively small.
Okay.
So instead of having a single central computer, we break it up all into different pieces and components. We basically build circuits for each function that we want to implement
Right.
individually, and maybe have a coordinating system as well. We build these in hardware. We can take the approach that we can design these on the ground. We implement the
Well,
GPUs. These are for very large neural networks of millions of parameters.
yeah.
We're not talking about millions of parameters. We're talking about just a few. And each circuit performs a simple function. So
Mm.
thereby we break it up rather than trying to have this huge, massive neural net, which is the current approach in AI.
Yes.
Um, so the question then becomes how big can we make these things? And that's still an open question. We've made just two neuron circuits. Instead of exploring how many circuits we can build, we've gone down another road. One of my students, I got her to build a back propagation learning algorithm in circuitry.
Oh, okay.
So I managed to show that we could get this to work for just a couple of neurons. Obviously, the back propagation circuit was pretty chunky, so that would not be very feasible for a larger neural net circuit. What I'd like to do is, again, in future work, we've delved a little bit into it with a couple of students, looking at how we can implement a neural net to essentially navigate a random rock field. So avoid obstacles and follow a path and so on. And the neural net we got to do that was relatively straightforward, was relatively small, hidden layer of 8 neurons, I think. So relatively modest. But one of the things I'm very interested in doing is to go a step further, which is, I'm pretty certain nobody's ever tried to do this before, is to try and implement a Kalman filter algorithm using neural nets. People have implemented various parts of a Kalman filter using neural nets, particularly the model, but no one's
Yeah.
tried to implement the entire thing in one or more neural nets. And that's one of the things I'm very interested in doing. And that has very interesting theoretical implications about the computability of neural nets. So that's just some rambling musings of some of the things we've been doing.
Very interesting.
And I haven't even mentioned that we've actually manufactured stuff from the Lunar Highland simulant. It's not got the same material as the Maria. It's mostly composed of a mineral called anorthite, which actually has aluminium in it.
Yes.
And so what we've done, we've experimentally shown in the lab that we can take a simulant of anorthosite, Lunar Highland stuff. We can separate out all the iron parts, leached it with HCl acid. It breaks it down. A replication of what happens naturally on Earth. When we have acid rain, so carbonic acid, it leaches into limestone and then just breaks it down. And one of the products of that is sand or silica.
Yep.
So we have a process where we take HCl leaching and that allows us to extract silica. Silica can be used in make fused silica glass, which is transparent and can be used for optical applications.
Yep.
We also have aluminium chloride, which I'll talk about in a second. And we also have calcium chloride. Calcium chloride, it's the electrolyte for the next stage of the process, which I'll come to in a minute. So the aluminium chloride is then heated and that breaks down to alumina and and water. So alumina, we've demonstrated this. We can put this into a molten salt electrolysis reactor and that will strip out all the oxygen. And that leaves us with, we basically extracted molten aluminium and then we stretched that out into wire. And that was then fed into an electron beam additive manufacturing facility, NRC, and 3D printed a small aluminium tank for holding oxygen.
Okay.
So we've demonstrated the entire process from going from this regular simulant to an actual aluminium tank. So we've demonstrated that we can use this for building structures. And of course, one of the beauties about aluminium is it's a multifunctional structure. You can use it for electrical conduction, for thermal conduction, for radiators, for mirrors, and all kinds of things. So it's a very versatile material. And that is really the key to how we actually implement our approach to trying to maximize multifunctional uses of different materials. So
Wow.
yeah, so we've been quite busy.
So it sounds fascinating. So when we talked earlier, we were talking about like mining on the moon versus mining on asteroids.
Oh
And
yes, we can get to that. Yes.
your take on which we should be doing?
Right. One of the challenges of trying to mine asteroids is the fact there's a milligravity environment and it's very difficult to get purchase onto
Yeah.
an asteroid. You need to have some kind of impact penetrator or something to basically anchor yourself into the ground. Where this doesn't work is when you've got things like rovers and so on and so forth, which can't be anchored into the ground because they've got to move around. Plus, if you're doing things like drilling, if you want to work on a drill, the major performance of the drill is dependent on something called weight on bit, and that depends on the heaviness of the drill. If you want to drill boreholes, and obviously you've got a very tiny weight on bit on an asteroid. This is actually a very difficult, challenging thing to do. You need to have pythons and all kinds of things to anchor anything down in order to process asteroids. The advantage of asteroids, of course, they've got a lot of materials that you can't get on the moon, or at least are very rare on the moon. You've got carbon and water and all sorts of hydrogen types of materials. Some of the near Earth asteroids are believed to be spent comets, and they will have a fair amount of things like nitrogen in them as well.
Right.
So it would be really advantageous to try and access some of this material. And in particular, when it comes to some of the nickel iron asteroids, they're a source of iron, which we have on the moon, nickel, not very much on the moon,
Oh,
cobalt, not very much on the moon. There's troilite as well, and troilite's an interesting one, which I'll come back to in a moment. We want to build everything on the moon. How are we going to get asteroids on the moon? It appears, we don't know this yet, but there appears to be evidence that over the eons, the moon has been impacted with metal asteroids over a period of time. And there are certain locations which seem to indicate there may be buried nickel iron material beneath the surface.
right.
And so, if we can access them, they're already on the moon. We don't have the milli G gravity to deal with. We've got the 1/6 G, which is much better than the milli G. And so, we potentially have extra access to asteroidal material on the moon or just under the moon. And now, the industrial architecture that I've been developing and the demandite makes the assumption that there is this material there because we can't build everything completely. We can't industrialize the moon without this kind of material.
Hmm.
So if we have nickel and cobalt, we can start to build a range of steels out of the iron that's already in the Maria. In addition, it also gives us options for multiple different types of aluminium alloys. And in particular, Alnico is dominated by aluminium, nickel, and cobalt. Actually, very, very high quality magnetic material. Not quite as good as rare earths, but they're still up there, far better than ferrites and iron. So you can start to get some of the high performance magnets, which you could potentially manufacture on the moon. And this is the key to building things like motors and magnetrons and various other things that you might want to build. So, yeah, there appear to be magnetic signatures for these. We don't know until we actually go there and actually start to bury under the
Yeah.
surface. We don't actually have solid evidence that they're there. There are signs that this material is there, but they're not actual direct evidence. So, to me, a high priority would be to do more detailed mapping of magnetic signatures on the moon to try and localize some of these where these deposits might be, and then start drilling.
Ah, it's great.
So,
Oh, hmm?
this doesn't rule out asteroid mining. I'm just saying that a
Yeah.
way to practice the technologies that we develop would be to do this on the moon and then deal with the problems of milli G later once we understand how to do the extraction processes.
So one person that I interviewed a few months ago, he's like, what we do is we build tracks along on top of the asteroid and then have little robots move on the track and hold on to the track when they're trying to drill.
Yeah, yes, that could work. Another option is to once you've built even a small borehole, you basically can then have a drill which basically works with kind of friction shoes. But it seems to be easier to do it on the moon. All we have to do is dig, and then we
Yeah.
can extract it. We've got a gravity field, a reasonable gravity field. We don't have to
Yeah.
deal with that problem. And it seems to me that it's easier to access on the moon than it is actually. I know you got the delta V issues, but to me, I think the milli-G environment does present some quite challenging difficulties. And if you're trying to develop mining, and I presume most people are interested in the platinum group metals, I think there'll always be people who are interested in it, in asteroid mining, and it sounds great, but the technological challenges are a bit harder than they would
Okay.
be.
So talking about like robots in space though, what about the
Yeah.
radiation? Start flipping bits in the robot's brain and it's going to get confused.
Yeah, there are various methods for doing this. A traditional method was always to use hardened electronics, built silicon on sapphire and things like that. That's very, very expensive. The only people who used to do that were the military, and the space world inherited that. But people don't do that anymore. We use a technique called EDAC, which is error detection correction coding. So we use software to detect where bits might have flipped,
Okay.
and then apply corrections. It adds an overhead onto your software. I think it's about 30% or something like that, but it can deal with a certain number of errors. Obviously, if you're starting to get physical tracks in the electronics, that causes major problems because then you get burnouts and things like that. This is something that we have to live with. Again, EDAC overcomes some of that. I think where this became a real issue is when when we were sending missions to places like Europa, where you're slap bang in the middle of the Jovian magnetic belts, which is very hostile. It's the most hostile radiation environment in the solar system,
Oh,
uh,
okay.
apart from the sun, maybe. Yes, this is quite a difficult problem. And so the most solutions are to have multiple computers cross strapped so you can try and detect errors. Another approach, actually, I would say, would be instead of doing that, we could use vacuum tubes, because vacuum tubes are actually, they're not entirely radiation immune, but they're certainly radiation tolerant.
Silicon?
Sorry?
Much more than silicon?
Oh, yes, much, much more, yes. There was a case of, I think, quite a few years ago, I think a North Korean pilot deserted and flew to a South Korean base or something of that nature. And he was flying in a MiG. And when the engineers crawled all over the MiG, they started chortling because it was all based on vacuum tube technology. But at the same time, in a nuclear war, they'd be the only things flying.
Okay.
The EMP would basically knock out pretty much everything else. So maybe not quite so primitive after all. We could go back to vacuum technology. And again, one of the advantages of doing vacuum tube based technology is that it will survive. It's much more tolerant of the radiation environment, particularly if you're working on the moon or anywhere in space, that is.
Right. So that's an extra reason to use the vacuum tubes for your neural networks
Yeah.
you were talking about earlier. Okay.
Hmm.
Tell me what's harder than it should be in what you're working on.
The biggest challenge, if we're going to be using the moon, we don't have access to plastics. There have been people working on 3D printing on the moon,
Yep.
uh, but they all require 3D printing regolith or creating some kind of cement. The problem with these approaches, they nearly all require some kind of polymer to bind the particles together.
Yeah.
And again, even if we're printing with ceramics, for example, well, I'll come back to ceramics. So without plastics, it's very difficult to create things like compressive structures and insulating structures and so on and so forth. The only option we have is ceramic material. We can create glasses, we can manufacture in glass, that's fine. But when it comes to doing some of the really high quality ceramic material, so for example, in our crucible, in our molten salt electrolysis unit, we had a crucible and that's made out of alumina. Now, well, I've already said we can get alumina from the moon. The thing
Yep.
is, how do we process it? How do we process it into a structure? And one of the challenges we have is how do you process ceramic materials on the moon? One of the issues about ceramics is they require very high temperatures to melt. If you
Right.
want to 3D print them, what you need to bind them in polymer first and then burn off that polymer. That's not an option for us because we don't have access to plastics. So the only thing we can do is to figure out how to melt this material. Now, we've done some experiments, not with pure ceramics, but we've done some experiments with regular simulant using Fresnel lenses. And so what we've been doing is we've been using solar energy to heat, to basically melt the regolith to create little structures. The problem is that when you've melted the regolith, you've effectively turned it into glass.
Yeah.
And that's actually quite brittle. It breaks very easily. So one of the challenges is how can we make ceramics more ductile and more tolerant and less brittle? And we haven't really managed to solve that problem yet.
So like fiberglass.
Yeah, fiberglass. Potentially, we could put in some reinforcement fibers. That's something we haven't done, mainly because we evolved from a robotics group, and so we don't have access to those types. So we can't make fibers. We don't have access to that kind of facility. Most of the stuff we do, we just build ourselves and then have a crack at it. But forming things like whiskers and fibers for incorporating into composite materials, we don't have that skill.
Right.
But yes, potentially we could, that is a road we could go down, but that would have to be with someone else because we don't have that kind of capability. So there are limits to what we can do.
Switching gears a little bit, how would you recommend somebody trying to get into the industry? So for like students who wanted to get into doing this type of work, what would you recommend for them?
First of all, you have to do some kind of scientific degree. My background itself, my first degree was in physics. My master's was in astronomy, and I switched to engineering for my PhD, where I did actually a PhD in space robotics,
Okay.
manipulator controls, controlling manipulators in space to fix satellites when they're in orbit. Well, if you're an academic, your career evolves over time. You just stick your nose in wherever you think there might be some interesting stuff to do. So I couldn't have predicted to you 30 years ago that where I would be now, what I would be doing.
Right.
But to stay in the if you want to get into the space field, you have to be single-minded. You have to focus on space all the way through your career because once you're out of space, it's very difficult to get back in.
Okay.
So I've been always absolutely committed to working in the space field. There have been a couple of glitches actually. I worked in a hospital for a couple of years as a kind of medical engineer. But you have to focus on your degree progression has to maintain itself within that field. Otherwise, if you're out of it, it's very difficult to get back in. And just follow your interest. Don't follow money. Money is not going to make you happy. It's not going to provide you with interesting work. Just be single minded about if you want to work in space, you stick to it. You say, I'm going to work in space, and that's all I'm ever going to do. And I've pretty much adopted that philosophy, and I have absolutely no regrets whatsoever. There's nothing more rewarding than working in the space field. It's a fantastic area to work in. There's always something new. I've had to learn, starting out as a physicist, becoming a roboticist. I've also had to become a manufacturing engineer and a chemical engineer. I've worked in astrobiology. I've had to learn about microbiology. It's just the whole of the universe is open to you. And that's an absolute privilege. And that's one of the wonders of working in this field because there are no experts. If you're an industrial engineer, it's unlikely you're going to work in the space field. People who actually apply have to learn how to do these things and then apply them to the space environment. So you're never standing still. You're always constantly learning new things. And that's what makes it so much fun.
Right.
I've just got a comment. I think this channel you're doing, I think is fantastic. And I hope it becomes very widely known and popular.